We got Dylan back again, and he's really good at VR. Um, that's all I had.
Yay. All right. Hi, everyone. Dude, I got the email here. Hi. Um,
Uh,
it's me again. I know you're probably sick of me already, but I got one last talk on some really cool stuff, more general, less specialized than the hardware stuff we did last time. So I think y'all will enjoy this one a bit more. And this one doesn't have like a price barrier either, so you could just get straight into doing this. This is something I've been doing a while, and it's a huge passion of mine. So I'm very excited to share with y'all how you can get started in doing this in sort of a uh, like people can do it, but usually people have trouble with like the structure or workflow or how to actually get started, how to choose a target, how to sort of progress through like its code base or its environment if it's like closed source. So today we'll be talking about that. So what is vulnerability research? It's a pretty broad term. It's more broad than even the broad terms you hear of in cyber, but it really is the act of finding a vulnerability, which doesn't necessarily include exploiting them. That's exploit development. So like, discovering a buffer overflow or discovering like, a heap out of bounds or a SQL injection in some FOSS, that's all vulnerability research, right? And that's kind of where the most literal interpretation of that phrase, that's kind of where that chain of compromise ends. Um, and yeah, and on simpler targets, that sounds like no big deal, right? Like if you get a CTF binary, you could probably find the buffer overflow in it. But in like real life targets that aren't meant to be attacked, like Bluetooth stacks and NFC stacks and browser engines and compilers and stuff like that, these bugs can be much more subtle. They can be hidden under thousands of functions, really deep and really complex state machines. And they can be a lot harder to find, especially when everyone's kind of already looking at them. Um, so one of the first steps you're going to want to do if you are getting into zero-day hunting is you're going to want to choose a target. And there's the list is like pretty much endless. You could go after kernel submodules. You could go after like specific entire protocol specifications, like the USB stack or something like that. Or you could go really specific, maybe some weird WordPress plugin, or buying just like a router for $4 from Goodwill or something and pulling it apart. But some of the main factors you really want to consider when you're doing this type of work is if you can like safely think you'll find something on it, basically. So I think the biggest thing on here, or the two biggest things on here, are probably how complex it is and who the vendor is. You want pretty complex software because that makes it harder on the programmer doing their job, right? There's a reason lots of zero days are in different codecs responsible for file processing, like H.264 and JPEG and all that. It's because file formats are super complicated, so parsing them is really hard, right? That's where you see all those embedded based zero days, like the Pegasus spyware used one, and lots of popular vulnerabilities have arisen from that. You also want to see, if it's actually a zero day, right? This is much different from pen testing. A vulnerability you might find on like a closed corporate network is not a zero day. It's just something affecting them. This is software that thousands, millions of people are using. How familiar you are with the sort of technologies you might encounter, just so you don't spend as much time sort of doing that initial setup if you don't need to. What type of bug classes could exist? For example, like Bluetooth, if you're looking at Android's Bluetooth stack, for example, when you're lower level at like the service discovery protocol and the refragmentation stuff, you'll be looking at a lot of C or C++. But when you get higher level and you start looking at the higher level protocols that handle different Bluetooth objects and whatever, you'll be looking at a lot of Java because of the J and I interface up there. And how easy is it to acquire? How easy is it to debug? And who is the vendor? Because some vendors can be mean. So you want to do a bit of like threat hunting and see if there's a vulnerability disclosure process with them, if they have like a history of doing that sort of thing and being nice, etc. That's a cool book. So Yeah, and just disclaimer: always practice responsible disclosure. The typical way to do that is you give the vendor 90 days after you notify them. And you can coordinate with MITRE and get the CNA who's responsible for the product you just found the bug on. And always do that. Just a little ethical disclaimer. And if any of you ever get really interested in this and need help with that, we can help you with that. I think like the first time I disclosed a CVE to MITRE was when I was in like high school. So like lots of interaction here with that, and lots of people in the club, including alumni, who've sort of dealt with that before. All right, attack surfaces and data flows. This is mostly a thing you'll want to worry about with more complex targets, like your kernel modules, like your protocol stacks, because data flows can sometimes not be too obvious. The picture I have here of this little graph, it seems pretty obvious, right? It's a main function, and then we want to end up in parse state string, so we have to go through all these functions where we're parsing an HTTP request and stuff like that. But sometimes it can be really horrible to get a data flow. You find what looks like an interesting sync in some code, say like a bad mem copy, and it's deep in some proprietary like USB stack, right? And USB is a great example because USB is extremely complicated specification. And you're like, how do I actually reach this vulnerable function? It can be tough. You might need custom hardware to send those USB packets, right? Because if you try to send that if I just try to send that from my laptop, depending how low on the stack it is, my own drivers might not even let me modify that deep down, right? So you sometimes need proprietary hardware. You sometimes need to set up proprietary environments to even run it, etc. So yeah, the example on here, how can I send a custom Bluetooth packet that hits a sync? Bluetooth is annoying. Bluetooth has a lot of different layers, right? From just reassembling packets all the way to like the highest level object-oriented, like object exchange layers. And that can be really tough. For Bluetooth, you will need external hardware if you're trying to send custom packets and stuff like that. So it can really help to just sort of map these data flows, because on their own, finding data flows are like a whole nother issue, right? And yeah, that can be tough. You'll be reading lots of specifications, going through lots of different functions and searching big code bases, and it can be annoying, but I'm going to show you some methods on how to deal with that. So the first one, I think this slide is a slide up too early, but we're going to start talking about taint analysis, which is just basically the process of finding sources and sinks, and a source being here, a sink being here, right? How do I get from the source to the sink? And the only difference with taint analysis is that everything tainted by our source is included in that flow tracking. So if I have like this variable x that is tainted, and later on y is assigned based off of something from x, y is also tainted now. And there are lots of good ways to do that. We're going to mainly be talking about the open source, or not the ways to work on open source sort of projects, because those yield the best results. And a lot of the larger targets will be open source, right? Android's open source. Lots the Linux kernel's open source. Lots of the larger things are open source, so you could use open source tools on them anyway. But this is just a random picture of I think it's pronounced Adrane. I'm not good at pronouncing things, but this is just it's one of the oldest plugins on Binary Ninja that does source to sync analysis. It's not really a call graph thing, even though it looks like that here. There's call graphs in Binja without this, but just does source to sync analysis. You could click on a function in Binja and right click it and treat it as a source or a sink and find its neighbors. So, okay, analysis with source. What we're going to be talking about today, you can do on CodeQL and SemGrep. I definitely recommend CodeQL if you're going to use either of those. Very good tool. I don't think it was made by GitHub, but it's owned by GitHub currently. and it's like a semantic database of your code. So you can search on like different semantic differences and vulnerable patterns and whatnot. So taint analysis, again, I said it's sort of source to sink analysis, but you could do it backwards too if you want. And this simple flow chart here, just an example, right? We're on a website, we have our item that we want to check out with. Later on, something else is assigned based off that item. So now we're tracking both. That is if the tainted item also ends up in a valid sink. And yeah, the goal is to find attacker controlled sources. So like that doesn't have to necessarily be like the source that gives you explicit like a read function, for example. It doesn't have to be the source that explicitly gives the attacker control, like a function that takes something from standard in. But you could use functions down the line that higher up you had control, like a function that translates streams into types or something like that from like packets. And you want to look for interesting sink categories, especially if you start looking at this code base a while and doing like threat research on like old vulnerabilities. You'll definitely find some patterns reemerging. Human habits like a hell of a thing. So a lot of the time you could make good sinks based on old vulnerabilities, which I'll get to later. The issue with taint analysis and sorts of analysis kind of like this are path explosion, right? Every time we hit a branch, if we're tracking a tainted thing, every time we hit a branch, we get 2 paths added to the path pool that we're analyzing, which grows exponentially. So to avoid that, it's usually good to do sink to source analysis, because source to sink, that will track what we're interested in, but that can also track a lot of really unnecessary tainted variables. But if we're going sink to source, we know that we're only tracking what we're interested in, because what we're tracking sort of ends up in the sink. Again, note attacker controlled sources and interesting sinks, and filter out uninteresting patterns and results as you go. None of the stuff I'm going to show you is like automatic pwnage, right? You still got to do the work yourself, and you may have like great sources and great sinks, but you may find like upon looking at it, you're looking at like this malloc call, and then earlier on it actually was bounds checked, or there was a sanitizer up there that sort of makes it unexploitable. So after you discover these patterns, you want to be sure to filter them out from future searches so that you don't continuously waste your time. Cool. Patch diffing and variance analysis. This sounds kind of like not too like something you wouldn't find all that common in real life, but you'd be surprised even when you're not doing patch diffing and you just discover a new vulnerability, that code pattern can reemerge everywhere. And a good vulnerability research practice just in general is just looking at the Git blame and seeing all the commits from this one guy, right, who's responsible. Because people reuse code, they have certain bad habits, and they might do the same certain things repeatedly, especially if they don't know that it's bad or they're not in sync with maybe other programmers working on the same code base, right? So taint analysis can be used to find data flows and sort of vulnerable patterns, but variance analysis can be used to sort of find what you're going to use taint and like how you're going to make your taint analysis queries. So a classic example is like patch diffing. You could patch diff the changed call site or the changed blob of wherever in the code base like was affected itself, and see like if their patch really fixed it or if their patch was like stupid, stuff like that. But like that also gives you, again, a really good idea of how people write code, and you can use that to make searches across an entire code base. And yeah, so variance analysis is kind of like creating these heuristics based off vulnerable patterns and searching for that pattern. So like if I see a new CVE come out for USB, a certain USB stack for a certain subsystem, then I might be like, okay, so The issue here is they allocated this object, but they didn't account for like the header and the size of the allocation. So you have an n byte overflow, and I can use CodeQL and tools similar to it to specifically search for semantic heuristics where they make an allocation call with that type of structure without accounting for the structure size. You can get super granular and specific and do queries like that. So the example on board here is CVE 2022-2410. That was a vulnerability in the Bluetooth stack for Android, and it was an integer overflow, and it was found using CodeQL. And I have the Black Hat talk linked here, but lots of these Bluetooth bugs, which aren't that, like they're old, but they're not crazy old, were found with just CodeQL, right? And these can be super dangerous. So like the bugs at the top here, I won't go too in depth into it, but basically you have this unsigned 16-bit integer over here, right? So, and you see that it's like basically initialized to have the value of 8, but then later an attacker controlled value, which is of the same type, is added to it, right? But the issue is there's already 8 in there and the attacker can control what's added, so they could just make that the max int 16 size, and then it overflows by 8 bytes. And you know, there's also another issue here, right, where they're only checking the upper bound. So when we do that integer overflow, we're actually negative, but when that gets passed to something like memcopy or whatever, which I'm just kind of, I didn't really read the bug just now, but like staying on that example, if it did get passed to something like that, it would bypass the size check, but then it would still be exploitable when it hits memcopy and is interpreted as a really large number. So those are two patterns you could look for. You could be like, and there's a CodeQL query right here that looks for basically values where the max left side of an expression is smaller than the right arithmetic. I think I'm not very good at reading CodeQL, but you could find vulnerabilities like that. You could find patterns like that, right? We could also make a query for the if conditional here that only checks the lower or the upper bounds, and stuff like that. Happens fairly often. People make really shitty design decisions and then keep doing it because, you know, they don't think it's wrong. So some binary analysis. So I'm sure you all know the difference. Code analysis, we have access to the code base, right? It's somewhere, and we're looking at it. But binary analysis, we don't. So this, you know, could be a whole talk on itself. But that's just looking at the binary without source. So it's kind of just reverse engineering, right? There are a couple more things you might not do in like a CTF challenge that you might have to do in real life, but it's just basic reverse engineering. So you'll need like a decompiler or something that lifts sort of the firmware blobs into readable sort of formats for you. And you'll just want to look for bad things. And a lot of these tools do also have you know, ways to do the sort of source to sink tracking. There is general like flow tracking from source to sink in tools like Binary Ninja and the like. And there are binary analysis sort of weird techniques like symbolic execution, which is like an SMT style, how do I get to this vulnerable thing or this thing sort of tool. But a lot of the times it's just good old fashioned looking, you know, especially if you're doing embedded VR. This stuff is super easy to find. You could just open, you know, a binary from a router in Binary Ninja and type in string copy and have like 20 0 days. So sometimes though, it just doesn't work when you actually get to the debugging part. For that router example, you know, that's probably running a reduced instruction set, and maybe I can't run the binaries on my computer. So this is where you're going to want to get into sort of environment setup depending on what you're doing your vulnerability research on, right? So a router, you know, I could use like QEMU user to emulate just the binary. I could do a whole QEMU system if I have the kernel image and emulate the entire system. Android, you know, you might want to buy an Android phone and root it and put OpenADB and whatever. But you need some sort of way to debug what you're attacking live, especially to confirm all these atrocious data flows. And again, just some examples like a router binary, you could use like QEMU. A Windows like sys file, you could use like killing or something. And then if you want to do like a specific blob of code, you could just use like Unicorn or some contextualist CPU emulator. Okay, fuzzing. Fuzzing's cool. It's a neat thing. And it finds a whole lot of bugs. Lots of the huge companies like Google and Android Red Team and they have fuzzing built into their software development life cycles. They have fuzzing continuously running on their own products, sort of trying to find things. And I'm sure a great majority of you know what fuzzing is, but in case you don't, it's basically, like just throw random shit, shit that's like kind of guided by your own heuristics, but still you keep throwing stuff until something happens. It could be like a crash. If you're going for coverage, you could use like AFL-cov to sort of use the sort of instrumentation that you built into your target to see if that input caused new code paths to be executed, right? So I'm going to mostly be talking about coverage guided fuzzing today, which when combined with sort of other subcategories of fuzzing is definitely the most effective fuzzing technique by far. There's there's other types of fuzzing. There's like black box based, like intelligent mutation fuzzing, and stuff of the like. But that stuff is not very effective these days as much as the code coverage is. So, and the reason for that should seem kind of obvious, right? If I'm looking at a USB stack, I keep going back to USB, but I'm having trouble thinking of things right now. Then that's probably been looked at by a lot of people, right? So all the really easy bugs, if they weren't found by the developers, they've definitely been found at some point. So you want to get really deep into the USB state machine and find things that haven't been really tested before. And that's pretty much the same with any complex protocol that follows a specification, right? And by the way, a good way to find bugs that's not even mentioned on this presentation is just looking at your stack and reading the specification. Because if there's something on the spec that wasn't followed or is just not adopted in the stack that's implemented, a lot of the times it's a security issue, because lots of the other people who base their clients and server-side stuff off of that specification are expecting certain things to happen. So just, keep that in mind if you're interested in doing the zero-day sort of research. But coverage guiding is a fuzzing technique, as I mentioned, that's based on executing new and interesting code paths. So how fuzzing works in general is you have like this initial corpus of inputs. They use a lot of weird terminology in fuzzing. I don't know why, but like you have an initial set of inputs. You feed it through your fuzzer sends it to a protocol, it sends it as a file, it does something, your target processes it. And then in the case of AFL++, it sort of instruments the target when you build the target using it sort of instruments extra sort of hooks in Clang and GCC. And when you actually send that input, AFL will record if any new interesting code paths were reached. And if they were, it will mutate future inputs based off of that and just try to get as deep into the sort of code into the code as possible. And it has a bunch of different methods it does this at. A lot of it's at the bit level. Surprisingly, doing stuff like bit flipping and whatever for mutations is extremely effective. You can run AFL++ on like pretty much anything and you will get a crash. It doesn't really mean it's exploitable, but or that it's not been found, or it might just be a non-issue. But its mutation strategy is very good. And the real power of fuzzing comes in when you guys are doing 0-day research and you implement your own fuzzers. So AFL++ as a code coverage and mutation strategy is extremely effective. But if you are targeting something, you want to make it more, you want to program your own sort of thing. And you can use AFL to do that. There's libAFL, which acts as like an API to use those sort of grammar mutators and stuff like that. But for example, if you're targeting some sort of driver on some obscure hardware, you could implement a tool that like gets that initial corpus based off of running normal packets against the driver, or not packets, but normal inputs against the driver, normal like ioctl calls, normal like sort of input calls, if there's like hardware interfaces you could hit that driver from and stuff like that. And then take that offline and use something like snapshot-based fuzzing, where you record all those inputs and then replay them in like scalable servers and sort of generate based off that inputs without having to interact with the hardware each time, right? Grammar-based you should definitely implement a grammar if you're targeting any sort of anything, pretty much. AFL++ on its own is, again, very effective, but you need something to sort of guide that guidance for the code coverage. And a good way to do that is by making sure you know the grammar extensively. And just basically the point of implementing a grammar is so you actually reach farther into the state machine by restricting values that don't really matter and that will prevent further deeper processing of your input, like PDUs or like just parts of the lower network stack or lower protocol stack or stuff you just know that isn't going to be vulnerable. You don't want that to be a part of your coverage guidance, and you don't want to waste time sort of having your fuzzer not get as deep as it can be because you're not taking the grammar into account. But yeah, AFL is cool, or AFL++ is cool. It's instrumented, it's coverage guided, and it mutates future inputs based on the coverage of previous inputs. It has a lot of forks and built-in modes, right? So I mentioned AFL++ is instrumented, but it, for example, has a unicorn mode where you could run AFL against like arbitrary binary fragments. So you don't even need the context of the entire binary because it just uses unicorn to sort of execute instructions in an isolated contextualist sort of manner. And this can also be very powerful when it's combined with sanitizers. So for example, if you're fuzzing like the Linux kernel, you could use a bunch of built-in sanitizers when you compile the Linux kernel that are compile time options to turn on stuff like address sanitization and like uninitialized sanitizations and stuff. And basically what happens is when a violation occurs, when you start fuzzing and you trigger like an invalid memory read or something, that CPU exception actually causes everything to abort and it prints out a bunch of information for you. So that can be very useful. You sort of don't think about it from a high level, but when you start looking into fuzzers and trying to build your own, you sort of realize that fuzzers have a lot of moving parts. You need something to sort of, depending on what your target is, restart that service if you get a crash. If it has to be like if it has to be some sort of network-based fuzzing, like strictly over the air, like maybe like baseband, right? You can't really get the firmware for that online. And a lot of the times you really just don't really have an option unless you're doing like snapshot-based fuzzing, but like fuzzing over radio, then you need a way to fuzz over radio. You need a way to have packets intercepted so you could mutate them and then forward them. You need ways to triage crashes, triage what's interesting, so all those sanitizers. And yeah, depending on how you're fuzzing, like if you're using just vanilla AFL++, you need a way to instrument that if there's a need to do any further instrumentation besides the Clang and GCC instrumentation. So AFL is a super extensive tool. That could easily be like a class at Mason if Mason taught like cool fuzzing classes. But if you guys are interested in doing vulnerability research, especially on more complex and looked at targets, like Bluetooth stacks, like protocol specification stacks, like Android, like Linux, I definitely recommend you start looking into libafl and protobuf and different ways to sort of build your own fuzzer. Yeah, that's a cool picture. Okay. Does anyone have any questions? I know it's a bit early. I was going to have a demo today. Like I was just going to do a CodeQL demo where we search up a heuristic on the Linux kernel and look at that, like look at one of the search results and see if it's bad. But I low-key did not think I'd finish this because it was 13 slides, but I zoomed through it. So, any questions, anyone? Yes, sir.
Will the slides be in the Discord?
Yes. Cool. Thank you all. Cool.